All right. And welcome, everybody. I'm glad you're here. This is an update on a heavy lift drone project that I've been working on. I thought perhaps to look at the concept of a heavy lift drone on a flying device that has already been created. And this flying device is the DeHavilland plane, the DHC-2. It had a wingspan of 47 feet and an overall length of 29 feet. The DeHavilland sold this plane design to Viking, and so now Viking is the company that actually makes it or keeps up with it. Viking extended the nose a little bit and put a Pratt & Whitney turboshaft jet engine in it. You can see that I have added to this DeHavilland Beaver is the name of it. The commercial version of these planes by DeHavilland were named after animals. They named one an otter. They named this one the Beaver. And I'll go to a different, this is very complex. It's hard for the computer to show this. I'm running it in SketchUp, so I'm going to go to a different version to show you how I modeled this. Okay, again, this is inside of SketchUp. Here is a photograph of the de Havilland as an Army plane, so it would be named the de Havilland DHC-2. Here's my version of it. And then I was able to find a specification drawing of it from various different views, and I just took my SketchUp and created a version of the plane that fits on the underlying drawings. See, there's the drawing. And then I decided I would make it this green color. This is a color that's available in SketchUp, and that's the color here. So that's where the de Havilland DHC-2 came from. And I've already done a discussion on the concept of using a bent axis hydraulic motor to spin the propellers. I've got extensive YouTube videos on that. And so this takes hydraulic flow that goes to this motor and it spins this propeller around. And the way that this hydraulic flow is created is through a turboshaft jet engine. And I'm showing that inside the de Havilland, the amount of power needed for the plane to just fly along is about 90 horsepower. But to get it to go straight up in the air with these propellers takes about 850 horsepower. So you can't, one engine will fly the plane, but you need two engines to make it go straight up. And these are just extruded aluminum tubes. I made them sort of aerodynamic. And this rear horizontal stabilizer may need to be strengthened because it's got this lifting force on it. That's what this support strut is. I wanted both propellers to be mounted on the same support strut. So this propeller is a pulling propeller. It pulls the plane up. This is a pushing propeller. And the reason for this configuration is I realize it's going to be useful if the propellers can tilt. And so I built this tilting structure, and it runs on two pistons. The reason I put two pistons in there is just for redundancy. And I can show you how this would tilt. So you can see that this support beam is holding up this holder, and this holder has a bearing. I don't think it needs to be a ball bearing. It could be a oil impregnated bronze bushing bearing, and you can put a turning controller inside SketchUp on the long axis of that bolt. And again, this goes a little bit slow. These propellers are complex, and SketchUp takes a little bit of time to show them, but this allows you to tilt the propeller down. And all that would happen, there's a 90-degree tilt right there. And you can see that these pistons are now fully extended, and that rotated this thing here. You can see here that they're fully retracted, and over here they're fully extended. And so you have the ability to create vertical power or vertical thrust or horizontal thrust. And this is a pusher propeller, so that when this one swings up, it pushes air back this way. And this is a pulling propeller, so it pulls up, and when you swing it down, it pushes the air back. And these two engines generate enough power to put this plane so it can go completely straight up into the air. And this is a SketchUp drawing where I created this a scale version of this hydraulic pump or hydraulic motor. And over here I created a this is the Allison 250 C47M turboshaft jet engine. It's now owned and manufactured and made available by Rolls-Royce. And just here are some images of it that I found. There it is. Okay, so inside of this plane, now I made the walls of the plane, I lowered the opacity of the walls so you can see through them. I got my little mannequin, he's about the same size as a human being, and here is this jet engine, and the turboshaft jet output of it is brought out and is turning these two pumps, and these two pumps, the output of these two pumps goes to this manifold system that controls the flow to the 6 propellers, so that you can individually adjust the flow to the propellers so that you have a stable hover. And here is a cutaway view of that manifold. I think it's going to be critical that you control these valves very precisely. That's what's going to allow you to have a stable hover. And this design is one of these pipes is the main pressurized flow, and the other pipe is the main return flow. So these two pipes are going to the pump system, and these 6 output pipes are going to the 6 different propellers. So there's 6 output pipes, there's the output pipes, and there's 6 return pipes. And this linear actuator is based on the ball nut ball screw system, except unlike what's normally done where the ball screw spins around, I'm holding the ball screw still and turning the nut. And this nut is turned using a servo motor that's geared down to spin the ball nut. And the thing about a servo motor is that you can attach a servo motor to a digital controller. So you can have a central processing unit running the itself to create solutions for what should be the valve position for the different propellers, and it can send that information to the digital controller of these motors, and the digital controller of these motors tells these motors what to do, and these motors adjust these stems of these valves up and down. And that, as you can see, as this stem comes down, it interferes with the flow, and as the stem goes up, it gives more flow. So you have the ability to have a very precise and measured control of the fluid flow to the hydraulic motors of the propellers. And so you can see inside of this DeHavilland, I have one of these turboshaft jets that's just running the pumps, and these pumps would actually send their output to be here's another turboshaft. So there's 2 turboshaft jet engines, there's 4 pumps. All 4 pumps would send their output to one side of this manifold, and all 4 pumps would receive their return flow from this manifold. But you only need one manifold to control the flow to the 6 propellers. So there's one manifold, 2 pumps. And the math is there. I will prepare a more complex YouTube video that shows one of the pumps is the VP1 pump by Parker Hannifin, because it has a variable displacement, so you can alter its flow easily. The other pump is the F12 125. You need 2 of those, and an F1240, you need 1 of those. And if you take the 850 Newton meters of torque that these jet engines can create, this shaft has 850 Newton meters of torque and spins at 6,016 RPM. This plane, it weighs 3,000 pounds and can lift 5,100. It can have a total weight of 5,100 pounds, so it has a payload of 2,100 pounds. So if it weighed 5,100 pounds, it can't weigh more than that. So you take these 6 propellers, and they have to be able to lift 5,100 pounds. And these propellers and pumps do add some weight to the plane. The total weight they add is 916 pounds. So the payload of this plane becomes 1,100 pounds instead of 2,000 pounds. But I don't think that's so bad. And this is an airplane that flies. It already flies. So you don't have to worry about, is this thing going to work? Because it already can fly. It's very famous. And all you're doing is creating 5,100 pounds of vertical thrust to make it go straight up in the air. Then what you do is you turn these 2 down so that they start making it go through the air this way. As it speeds up, it needs to get to be about 60 miles an hour, which is not very fast. Lift from this wing will be equal to 5,100 pounds, and you can turn these off. They don't have to do anything. Now, these are 2-meter propellers. They're optimized for static thrust, so they have a pretty fat cord. And I think if the plane is flying along just dragging these propellers, the drag effect is going to be too much. And so my thinking is to tilt all 6 propellers up. These 2 propellers are making 45 horsepower each. That's what you need to get the plane to fly through the air. These other 4 propellers are, and that's at maybe 1,600 RPM. You need 2,300 RPM to get enough thrust to go up in the air. That's about 800 horsepower. Well, you only need 90 horsepower to make it fly along, because fixed wing flying is so much more efficient. So these might be turning at 1800 RPM, but these four, I'm going to suggest for them to turn at maybe 100 RPM or 112 RPM. What you want to do is have them turning just fast enough that the thrust they are creating is equal to the drag that they are creating, so that they have actually no net effect on the plane. And they're just there, riding along for the ride. And I guess now some of your 1,100 pounds of payload might be fuel. I can't remember if the 5,100 pounds includes fuel or not, but to me, that's pretty nice. That's a nice heavy lift drone. And by the way, if you have a power failure or something's not behaving correctly, this thing can be landed on a runway like an airplane. And there is, Pratt & Whitney makes the, okay, here we see is the Pratt & Whitney PT6B-37A turboshaft jet. It has a output shaft 4,460 RPM at 1,400 Newton meters, and you really need more power than that to get that DHC-2 DeHavilland into the air. Here's what that Pratt & Whitney looks like, and here is, again, I kind of took my Rolls-Royce engine, the Allison 250, and mushed it around to get it to be about the same size, be a duplicate of the Pratt & Whitney. And then here are, here it is. There's that Pratt & Whitney inside of the DHC-2 deHavilland. And there is, this is what's considered a 900 or 1,100 horsepower Pratt & Whitney. They say that Pratt & Whitney makes whatever horsepower you want, including a 2,000 horsepower, but it's like the unicorn. Everyone talks about it, but I can't find any pictures of it, and I can't get any Newton meter and output RPM specifications on it. But there's a possibility that you could get one jet engine and get this plane in the air, and that would be pretty nice. But this is just a brief introduction. I'm going to do a series of YouTube videos to discuss all of this further and in more detail, and do the math and show you the math to demonstrate. I mean, obviously I have not created this plane, but the math says it will work. And what's really interesting is Viking modified this plane so it can carry 6,000 pounds. So if I can find the mythical Pratt & Whitney 2,000 or 2,200 horsepower turboshaft jet engine, we might be able to get this thing in the air with a 1,200 to 1,500 or 1,800 pounds of payload. And that's pretty cool. All right, well, I was disappointed that the de Havilland needed two engines, and I thought, well, just get over it. And I went out and found the Cessna 172, which is a much smaller plane. Not much smaller, but it's a smaller plane. I think that the DeHavilland was 44 feet this way, and it was 30 feet that way. And using the calculations, as I explained before with the DeHavilland, you have to work out what you need to get it to work. And we're using the same propellers that were on the DeHavilland. These frames are a lot smaller because this whole plane it doesn't weigh 5,100 pounds fully loaded. It weighs 2,500 pounds. So these support structures don't need to be as big. And but it's the same propeller. The motor needs to be the F11-14 motor. What you do is you take the F11 motor is the Parker-Hannifin saw motor. It's used for sawing wood. So it's a very high RPM motor, but it's not very big. And so you can connect that high RPM saw motor to a Framo Morat GSB-120 speed reducer and cut the RPM of the motor by 4-to-1. And that combination is less heavy than just getting a Parker-Hannifin motor. And you only need 1600 RPM in these propellers to get this plane to go vertically straight up. And the pump that you need, again, is the VP1-130, the variable displacement pump. And in addition, the Parker-Hannifin VP1-130 pump and the Parker-Hannifin F1260 pump, because you need a high flow system to get it to go straight up in the air. But once it starts flying, again, you rotate this down. You only need 60, maybe 80 horsepower to get this thing to fly through the air. I took these propellers and duplicated them to get the up and down and left and right circle that this propeller will spin in. And I also rotated the propeller down. So this is the sort of ball of space that this propeller needs to occupy in order for it to do its work. And I'm not completely sure how to do this. I don't mind this. It does put the lift sort of where the weight is. The weight is more here. There's another configuration where you take this propeller and move it over here and connect it to this horizontal stabilizer. And you don't want it to, I think, yeah, this is configured as a pusher propeller, but you really would want it to be a pulling propeller. There's a cheater's way to do this. It's not completely correct, but now it becomes a if you turn it around, it would pull it along. And the problem with trying to get it up in front of here where it pulls it along is that all of this begins to interfere with all of that. So we have to not do that. And let it be a pushing propeller. And it would be resting on this horizontal stabilizer, and you would be going, well, yeah, but you can't do that because this would crash into the ground if you landed. But it would not crash into the ground all right, so I got this to a more clear view, and you'd have to talk to pilots. If you laid this support beam directly onto this horizontal stabilizer, if the propeller was in the pushing mode, you're going to hit the ground with this tip. But if you swung it down so that it was in the, so this is horizontal thrust mode, this is vertical thrust, then it would have some clearance off of the ground. This I can't quite measure this because the way you draw this, you're better off drawing it with magnification. So this is going to show 1100 inches, but this is times 100. So it's really 11 inches. And I think the pilots would tell you that's too close to the ground, 11 inches, which means that what you're going to have to do to get this to work is to elevate this, let it be a pushing prop, and elevate it. In this kind of a configuration. And then when you're landing, it's not going to be that close to the ground. But you dramatically increase the length of your plane, and you have all this lift way back here in the back of the plane when most of the weight is up here. And the only reason I'm showing you this is just to make the point. We're not arguing about power and batteries and electric motors and enough battery to get it to fly for hours and hours. We have the power. Now it's just the design of the plane and taking the parts and putting them where you want them. I still feel like this is probably going to wind up being out here. This thing is it's going to be like a B-17. But I just wanted you to see that you can do it with the Cessna, and all you need is one of the Rolls-Royce Allison 250-C47 engines. You don't need two. And I thought I would, at the end of this video, just show you some of my other videos on the heavy lift drone. It's fundamental to the heavy lift drone that the propeller can get the drone up into the air. So my YouTube channel has this heavy lift drone propellers. And this is the link for it. The next in my series is heavy lift drone power management, where I show in more detail about how I created this image of that jet engine. And here is the YouTube address for that one. Again, that was heavy lift drone power management part 1. Heavy lift drone power management part 2 was the next one. So power management is just showing there's enough power to get the drone up in the air. I have a third or fourth set of YouTube videos I'm going to do to show how you modulate the power to get a stable hover. I haven't done that set of videos yet, but here is the YouTube address for that third video that I made. And so, you're welcome to go look. Those are long videos. I like making long videos. YouTube keeps telling me not to do that. So I'm going to make a series of short videos. But those are the ones where I'm going to demonstrate that you can get the drone to be in a stable hover. It seems to me you want to get a propeller that will get the drone up in the air. Then you want to show there's enough power to get it up in the air. Then you have to show the real actual parts that allow you to do it. And then you have to show how to have a stable hover. And you'll notice that none of this is electric. The problem with electric is right now, you just can't work with 900 horsepower or 1200 or 2000 horsepower. There's nothing electric that can do that. But this can. The jet engine exists. The pumps exist. The propellers are easy to make. The motors, it all exists. The only thing that doesn't exist is modulation of the thrust of the propellers. But I think the manifold and valve system I showed you will do that. So anyway, more to come. And we're glad you're here. Thanks for watching.